All right, you guys. And so now for number 7, well, we just start with section B. And for number 7, we have the function h. And so this function h is defined by h of x equals this whole thing. For x pertaining to all real numbers. That is what this is telling you here. So x pertains to all real numbers. That means that everything in between you have, I don't know, you have -1, you have -1.05, you have everything in between. Okay? All right, guys. So blah blah blah, they tell you that it has a local minimum at point A. So this is a massive sort of hint when we're talking about a minimum. We'll see how that comes into play later. That being said, for part A, you need to find the value of the y-intercept. So the value of the y-intercept, I'm sure that some of you can look at this and immediately say, ah, lol, yes, this is y equals 3. Or this is 0, 0.3. And a lot of you have that intuition because it is what doesn't have x next to it. And so you have h of x equals 2x times e to the power of x plus 3. And you say the y-intercept is 3 because it's the only one that doesn't have an x. And I would say, yes, you are right, but let's also understand why. And actually, you need to do this for a method point. Just putting this gives you 1 point. For the other point, you need to use the method. So you probably have this intuition because you've been taught that the quadratic formula, this c, okay, this c is the y-intercept. You were probably taught this and you never forgot it, but maybe you didn't understand why. And so the y-intercept, what do all of these points have in common? So all of these are y-intercepts, but what do they all have in common? For example, this one is 0, comma, negative whatever, 4. This one is 0, comma, 10. Okay, I'm just making numbers up. See, this one is 0, comma, 12. What do they all have in common? Ah, all y-intercepts have an x of 0. And so whenever, ladies and gentlemen, you are trying to find a y-intercept, you just need to plug in an x of 0. So let me write that up here real quick. Basically, for x-intercepts, it's always going to be some x, comma 0. And for y-intercepts, it's always going to be 0, comma some y. And so for y-intercepts, you need to plug in 0 for x. And for x-intercepts, you need to plug in 0 for y. And with this golden rule, you can find all the intercepts you ever need in your whole life of math. And so for part A, because it's a y-intercept, we need to be plugging in 0, comma y. So if you plug in 0, comma y, well, this whole thing is y, so this whole thing is just going to stay as y. And y is going to equal 2 times 0 times e to the power of 0 plus 3. And so because this first term is times 0, it's just going to be 0 plus 3. So that is why y equals 3. And basically what this is telling you is that you have the point 0, comma 3. All right. So that was just a small and quick explanation for how to find intercepts. Okay. So for part A, it's just going to be 0, comma 3. For part B, they tell you to find this. And so this, ladies and gentlemen, well, tell me what it is. Two things could have come to your mind. Well, technically 3. First of all, you could have said, I have no idea. Second of all, you could have said, this is the inverse. And third, you could have said, this is the derivative. Okay? How do you know which is which? The inverse would be with a -1. The derivative is with that small apostrophe. Okay, so here we're talking about the derivative. And so for finding the derivative of this, we can just go ahead and try it. And so here we have h of x equals 2x times e to the power of x plus 3. And so if you go ahead and do the derivative of this, we encounter something interesting. And so here, and Davey loves to do this, you have two x's interacting with each other. Technically, you have this first term here and this second term there. Okay, so it's very useful, especially for these scenarios, to think about it as two different terms. I know technically it's one term because it's being all multiplied together, but let's split it in half just to make this a little bit more friendly. Why is it important to do this? Because when you have two x's being multiplied closely together, technically you're walking into the product rule. And so the product rule in derivatives looks absolutely nasty. But really, if you take a closer look at this, okay, really here it's saying that, okay, in some function you have u times v, okay? And so if you do the derivative, basically, on the one hand, you will first leave u, whoops, let me pick a color that actually works here. So first you will take u and not touch it, and multiply it by the derivative of the other one. And then you will take v and not touch it, and multiply it by the derivative of the other one. And so now suddenly becomes a little bit more friendly. Basically, you touch one side and not the other one. Then you add and you flip it. Then you touch the other side and do the derivative of the other one. See? Now I know that was a lot of blah blah and it probably sounded hella confusing. Let's see it in action. And so on the one hand, you will first leave 2x untouched and multiply it by the derivative of e to the power of x. Now, what is the derivative of e to the power of x? E to the power of x, you can know it by heart, or you can just use the formula booklet. Remember, you guys, the formula booklet has a bunch of stuff inside of it, so might as well get to know what's in it, because the day of the test, it is an additional tool that you can use, okay? So once you study with the formula booklet for a little bit, you will remember, there's a section with derivatives, and you're going to look for it, and boom, you're going to find derivative of e to the power of x. So if you do the derivative of e to the power of x, you end up with e to the power of x. Yes, that is kind of troll, I'm not going to lie, but this is a formula booklet. You got to trust it. You got to believe in the process. And so right now, this 2x that I wrote down is untouched. Okay, I did not do the derivative of this first half. Okay, this is my u. I'm not touching the u. All right, but I do have to do the derivative of e of x, and I just found out that the derivative of e of x is quite simply e of x. So this first part is a little bit troll, I'm not gonna lie. See? Now I need to add and doing the derivative of this one and not touching the next one. So the derivative of the first one of the 2x is just going to be 2. How do I know this? Because 2x is the derivative of, is it not here? That would be crazy. Here it is, derivative of x to the power of n. And so as you can see, when you have the derivative of x to the power of n, which is basically just some x that's alone. Whoops, right now it came back. All you really have to do, okay, is notice, focus on the n. So the n first goes in front and then gets a minus 1. So for example, 3x squared is going to be 3 times 2 times x to the power of 2 minus 1, which is just going to be 6x to the power of 1, which is just 6x, okay? And so if we have 2 times x, is you have a 1 up here, right? So it's going to be, this is going to go in front, so it's going to be 2 times 1 times x to the power of 1 minus 1, which is just going to be 2 times x to the power of 0, and anything to the power of 0, ladies and gentlemen, is just going to equal 1. So this is 2 times 1. Oops, that is not a 1. Ends up as 2 times 1, which is just 2. Bada bim, bada boom. So over here, the derivative of the first one is just going to be 2, and the second one I do not touch it because of the product rule. If I go back over here, this is the one I'm not touching. See? So I'm not touching the second one that showed up, right? My v. I'm not touching e to the power of x. I just leave it as it is. And the plus 3, what happens to it is that it disappears, okay? Whenever you have a constant, that constant is going to disappear. The hardcore mathy explanation is that technically there is an x to the power of 0 here. And so here, this 0 would multiply in front. You end up with 3 times 0 times x to the power of 0 minus 1. This whole thing is just 0. See? So that is the hardcore math explanation. But I think we should just stick to the idea that if it doesn't have an x, it disappears. Okay? So boom, there is the derivative of h of x. That is for part B. And for part C, they put a very important word. They say hence. Whenever you find hence in the IB, it's a massive hint for what you used earlier, you have to use now. And so whatever you use from part B or part A, but most likely the one that was right before, so part B, you need to use what you had from part B in part C. This is worth mentioning because a lot of times exercises are set up like that, okay? And so it's a massive hint for what you need to do moving forward. So hence, find the coordinates of A. What the heck was A? That's what I mentioned earlier. A is the local minimum at point. A is the local minimum, which is right here. And so how in the heavens does the derivative help me find point A? Well, point A is a local minimum, right? And so why is the derivative useful? Why do people use it in the first place? Ladies and gentlemen, whenever you have, for example, you have something like f of x, see? F of x equals, I don't know, x squared, I'll make it up, see? So f of x equals x squared. So, from here, you guys, if you plug in a value for x, you get a value for y. For example, if you plug in, I don't know, 0, you get 0. If you plug in 1, you get 1. If you plug in 2, you get 4. If you plug in 3, you get 9. See? And all of these, you guys, are different sets of points. So this is without derivative. So without derivative, you get a bunch of different sets of points. With the derivative, it's a little bit different. So with the derivative, here I end up with 2x. And so with the derivative, it's not a set of points anymore. It's actually, you plug in an x, and you get a slope. Damn. So if you plug in 0, the slope is 0. If you plug in 1, the slope is 2. If you plug in 2, the slope is 4. If you plug in 3, the slope is 6. What? What is this? Guys, whenever you do the derivative, suddenly you're not getting points, you're getting something a little bit different. So for example, here, it's at 0, my slope is 0. Here it's at 1, like x equals 1, my slope is 2. So on and so forth. So this is x equals 2, slope 4, and this one is x equals 3, slope 6. And this actually makes sense because if you go ahead and look at the graph of x squared, which is which I'm going to show you in just a second. Yeah, so if you look at this function here, it makes sense because we said, okay, at x equals 1, for example, our slope we said was, where is this? At x equals 1, our slope is 2. At x equals 2, our slope is 4. And so here, it makes sense to have a slope equal to 2 because it's positive and it's growing. And that x equals 2, would you say that it's growing much faster? I would say that it is. So that's why the slope is bigger. See? And it's the same over here. If you plug in, I don't know, negative something or whatever, for example, let's do it. If you plug in x negative 1, you end up with a slope of negative 2, which makes sense because a negative 1 in my graph, and negative 1, my function is decreasing. Okay, so basically what I'm trying to tell you guys is that the derivative is super useful for finding out slopes, see? And so how can a slope help me find a minimum or maximum? Well, because if you take your quadratic, right? So if you take, or any function really, actually even here, see, I'm going to do it here. So here, if you start like writing down the slopes, for example, this slope here, I'm going to make it up, but it's probably like a slope of 3, see? This slope over here, it's a little bit less, it's probably a slope of 2. This right here, it's probably like a slope of 1. And at the minimum, what is my slope, you guys? Da, 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 da. It's a horizontal line. It's a slope of 0. So this is massive. Whenever you need to find max or min, derivative and equal to 0 gives you the x value. Because if you put the derivative equal to 0, basically you're doing the question the other way around, right? You're saying slope 0, what's x? That's what you're asking. So if the slope is 0, what is x? The minimum and maximum always has a slope of 0. And so for finding the coordinates of a, you're going to take your derivative and equal it to 0. So let me make a little bit of space because it's about to get a little bit juicy. So here we go. So if you take your derivative and equal it to 0, you end up with 0 equals 2x times e to the power of x plus 2 e to the power of x. All right, this looks kind of crazy, right? So what can I do from here? Well, technically, the e to the power of x is in both of my terms. So you can actually divide by that. Okay? Now, if it's hard for you to visualize it, let me show you to this way. Technically, you can factor both sides, both terms by e to the power of x. So you end up with e to the power of x times 2x plus 2. And from here, you can divide by e to the power of x, which is the same as doing it earlier, but maybe it's easier for us to notice. And so basically, you end up with 0 equals 2x plus 2. And so if you want to get x alone, you of course got to do minus 2 minus 2. You end up with 2x equals negative 2. You end up with x equals negative 1. Okay. Sorry. So I just found out that this right here is negative 1. And so my point A is negative 1 comma something, right? Negative 1 comma something. How can I find that something? I need to plug in negative 1. But careful. Where do you plug it in? If you plug it into the derivative, what are you asking for, guys? If you plug it into the derivative, you're asking this derivative function, when x is negative 1, what is my slope? And right now, that's not what you're looking for. What you're looking for is the corresponding y value. See? And so for the x and y values, we said earlier you have to use the OG. See? You have to use the OG. For slopes, you use the derivative. Okay? So we go all the way back and we use the OG. So I can plug in h of negative 1 into this one here. See? So you end up with 2 times negative 1 times e to the power of negative 1 plus 3. So I can work this out a little bit. This first part is just going to be negative 2. And this e to the power of negative 1, anything to the power of negative 1, or better said, anything with a negative exponent, you're going to flip it. So it's going to go on the bottom and still to the power of 1 plus 3. And so from here, because you don't have a calculator, you can just leave it as negative 2 divided by e plus 3. All right, and so this, believe me, is your final answer. Okay, and so the point A has an x coordinate of negative 1 and a y value of negative 2 divided by e plus 3. That is for part C. Just a quick reminder, you guys, e is an actual value. E is like 2.7 something, okay? E is an actual value, and the reason it exists is because it's a little bit like the opposite of the natural log, okay? It's an actual value, it exists, it's no different than pi, all right? It's no different than pi. E actually exists, okay? So take it as just a number. This can be your final answer. It's not like an x, it's not a variable, it's a number, see? So leaving your answer like this is completely legal. If you still don't trust me, I get it because I'm a guy on the internet, but look at the final answer here. Boom. You can leave it with in terms of e or just with e because e is indeed a number. So that is for part C. And now for part D, it gets even crazier. And so here it says show that, so it's something that is true, show that this occurs. What is this? And so here you have this double sort of apostrophe, see? And so basically it is the derivative of the derivative. Dun. That sounds kind of crazy, doesn't it? So basically, you gotta do the derivative of the derivative. So this guy that I have up here, right, I need to do the derivative once again. And so let me make a little bit of space. So basically, I need to do the derivative of this thing again. So from here to here, I do the derivative again. And I already know what's the derivative of this whole thing from part B, right? So the derivative of this whole thing is just going to be 2x times e to the power of x plus 2 times e to the power of x. See? So that is the derivative of that whole thing. Okay? It is straight from part B. It's nothing new. It's the product rule and all that stuff. See? And now I need to do the derivative of this second term over here. See? And so the derivative of that, well, we already saw that the derivative of e to the power of x is quite simply e to the power of x. So here you end up with plus 2 times e to the power of x. And so this is what you end up with. Okay? Now, we're not quite done because in part D, they're asking us to leave it in this sort of form. And so to leave it in this sort of form, once we already did the derivative of the derivative, we need to organize our values a little bit, right? And so the main hint that I can notice is that, they're factorizing by e to the power of x. So I should probably do the same. So you can do this later, you can do this now. I'm just going to do it now because maybe for some of us it's easier to like comprehend it. So if you go ahead and do it now, so if you take e to the power of x out of every single term, this first one is going to be 2x. The second one is going to be plus 2, and this third one is going to be plus 2. So you end up with e to the power of x times 2x plus 4, which is exactly the same as what they have down here. So that is for part D, part I. Then we need to do part D, part double I, and it asks us to find the values of x for which the graph of h is concave up. Alright, you guys. And so this is an awfully specific thing that you pretty much just like have to learn. Okay, I don't like to put it like that, but unfortunately it's true. I'm pretty sure this is not in your formal booklet, and this has to do with the buzzword concave up. And so there's two big hints for what you need to do. On the one hand, part D has two parts to it, right? It has part I and part double I. And whenever you have part I, part double I, they are always related, okay? And so to find the part where it is concave up, you need to use the derivative of the derivative, okay? And this is the sort of thing that I'm just going to tell you, okay? For concave up, so concave up, you're going to be doing the derivative of the derivative being positive. And for concave down, it's going to be the derivative of the derivative being negative, okay? I know that the derivative of the derivative might be a little bit hard to explain, so let's try to explain it now, see? So we said that the OG gives you x and y values, see? We said that the derivative now gives you slopes, see? And so the derivative of the derivative, what it gives you is sort of like the slope of the slope, which I know sounds crazy, but it's basically the rate of change of your rate of change. So for example, over here, right, all of these are positive, see? So all of these have a positive slope, but the question is, are they growing faster or slower? Here they are growing faster, so that means your derivative of the derivative is positive. Over here, you have a negative slope, right? But technically, it starts growing positive more each time, see? And so it sort of has to do with how fast your slope is changing, or in what direction your slope is changing. And so from here, okay, from here, you can go ahead and, as I said, do the concave up being positive to 0. And so you take this whole thing. I'm really running out of space here. I'm sorry, you guys, but let me make a little bit of space up here. I think it's going to be fine. Let me use a very different color just so that we're all on the same page. Right, awesome. And so from here, let me take, I don't know, maybe dark blue. See? So from here, the concave up, I said, was the derivative of the derivative being greater than 0. And so if you do that, right, so this being greater than 0, that means that this whole thing, e to the power of x times 2x plus 4, is greater than 0. See this whole thing, right? And so first things first, because you have e of x multiplying, that means you can divide here. And boom, something very similar to what we did earlier. This goes away with this. 2x plus 4 is greater than 0. Get x alone. Minus 4 to both sides. Bada bing, bada boom to get x alone. So 2x is greater than negative 4. Divided by 2, divided by 2. X has to be greater than, okay, it has to be greater than negative 2. Okay? And so basically that would probably be like around here, if I were guessing. So around negative 2, it starts going concave up. See? The slope sort of like starts like growing more. See? That is the sort of way you can think about it. I know that the derivative of derivative is kind of trippy and it's a little bit hard to explain, but I think the biggest intuition I can share is how fast your slope is changing. Okay? Because many times you can have a function maybe that looks something like this, right? Which you say, it's always growing, it's always positive, but each time it's growing less and less. And so this is a very good example of how, yes, you have a positive slope, but your slope is each time growing less and less. And so the double derivative here would be negative, because each time it grows less and less, but the derivative is still positive because the slope is always going to be positive. So that is maybe a better example of what I mean by the derivative of derivative. It's sort of like the direction your slope is taking in terms of growth. See? So if it's growing more than before as you travel through the x-axis, then okay, it would be a derivative of the derivative being positive. So for example, this here, I'm just going to finish giving the examples because I think it's important to get it, ¿cierto? If you have something that looks like that, like an exponential function, you would say, okay, the slope is definitely positive because all along the line it keeps going positive, and also the derivative of the derivative is positive because each time it grows faster and faster. Maybe that's the keyword I can give you guys. So for derivative, it's like speed of growth. So if it grows each time faster, it's going to be positive. And if it grows each time slower, it's going to be negative. All right, you guys? So that is the main idea I'm trying to like portray to you guys. And that is actually how you solve number 7. And so your answer for part D, double I, is just going to be x greater than negative 2. And your method points were doing exactly this. Concave up is taking the double derivative and making it greater than 0. Ladies and gentlemen, that is number 7, and I hope it helped.